All right, section 4.1, video 3, 2 examples left. Neither one of these will take extremely long, but with each example, we are doing all 4 of our approximation methods. So we'll do a left, a right, a midpoint, which are all rectangles, and then our trapezoids. All right, so there's a reason I gave these in particular problems, because there's something special about each one of them. So the speed of an airplane in miles per hour is given at half-hour intervals in the table below. Approximately how far does the airplane travel in 3 hours, in the 3 hours given in the table, and how far is it from the airport? We're not even going to worry about that because we don't know anything about where the airport is. Okay, so elapsed time is given in 30-minute intervals, and the speed is given in miles per hour. If you didn't already recognize it, you need to watch for things like this. The speed is given in miles per hour. The time is given in minutes. Those things are different time intervals. So what we need to do is change one into the other. By far, it's going to be easier to change the time of minutes into hours as opposed to changing the miles per hour into terms of miles per minute. So let's change the hours into minutes. Well, 0 minutes is the same as 0 hours. That's not a problem. 30 minutes is half of an hour, or 0.5 of an hour. 60 minutes is 1 hour, and so on. 1.5, 2, 2.5, and 3. Now we can use the time intervals as they are. Okay, that's really kind of the main trick here. Everything else is going to be relatively straightforward. Let's go ahead and I'll do the left approximation method first. Again, it doesn't really matter which one you do first. So let's see here. The left approximation method, every single one of my intervals is going to be 0.5. That is the base of all of the rectangles. The height of the rectangles, because it's a left approximation method, will mean that the left-hand part is going to be the height of the rectangle. So there's the first one. That's going to be the second one. The only one we won't use is the last one for a left approximation. Adding all that stuff up and then multiplying by 0.5 gives us 1,145. And remember, what we were trying to find is the total distance traveled, so that would be in miles. Okay, let's do the right approximation method. So once again, the base of all the rectangles is 0.5. In this case, we are going to use only the right sides of these things. So we're going to use all the ones in red. Only one we won't use is the very first one, because that's going to give us all of the upper right-hand side of the rectangles as our y values. So adding all those up and then multiplying by 0.5 gives us 1,130 miles. All right, so the one that's going to be the most difficult to figure out, because we're going to have to do the averages. I am actually not going to write all of the averages out. You guys can figure that stuff out. But the midpoint, so it'll be 0.5, then you'll have to average 375 and 390, then you'll average 390 and 400, and then 400 and 390 all the way down to the end. So you're going to average those midpoints. I will tell you that the answer should come out to be 1,137.5 miles. And as you can see, that's in between the left and the right, and that's pretty typical of a midpoint. Not always, but typical. And then the trapezoid method. Okay, this one I will at least write out for you. Remember, it's 1/2 the sum of all the bases times the heights. The heights in this case are the elapsed times, which is going to be 0.5, so those are all the same. And then we only need to add up the first and last base once and all the interior bases twice. So we're going to get 375 plus 345. That's the first and the last ones. And then all of the interior bases get added up twice. So it's twice of 390 plus 400 plus 390 plus 385 plus 350. And if you were to add all that stuff up correctly, then believe it or not, yes, you do get 1137.5 miles. Okay, and this works with the midpoint and the trapezoid that way because of the fact that they are the bases, or in the case of the trapezoids, the heights, they're all the same. They're uniform. Okay, that's why that's working out to be that way. All right, so again, you can plug in the stuff for the midpoint yourself. Let's look at example 7. The interesting thing here about number 7 is we're just going to approximate the area under the curve using the 4 different methods. The biggest thing is, and this is going to answer question 2, how is this problem different from example 4? Look at the x values. They are not uniformly the same distance between them. The first one goes from 1 to 2.5, that's a difference of 1.5. Then from 2.5 to 3, that's a difference of 0.5. So basically, the bases of these rectangles are all going to be different. The base between that rectangle is 1.5. The base between that rectangle is 0.5. The base between 3 and 5 is 2. And the base between 5 and 6 is 1. So the bases of my rectangles are all different. Now, the function is still x squared. So I'm still going to plug these x values into x squared to get the heights. Now, we're still going to treat it the same way, but I can't just pull the bases or the the one uniform base out to the front. We have to do separate rectangles for every single one. It's a bit of a pain, but it's not horrible because we only have a few values. So when x is 1, y is 1. Okay, let's use a different color for that. When x is 2.5, we've done that one before, believe it or not. That was going to be 6.25. When x is 3, it's 9. When x is 5, it's 25. And when x is 6, it's 36. Okay, not too difficult of values right there to work out. So let's go ahead and do our left-hand Riemann approximation. So if I use the left-hand Riemann approximation, the base of the first rectangle is 1.5. The upper left-hand side is going to be the 1, right? That's the left hand of that rectangle. And then the base of the second rectangle is 0.5. And here is my second rectangle. Here's the first one. Second rectangle, the upper left-hand part is 6.25. Not 0.625, 6.25. Then the third rectangle, the base is 2. And the upper left-hand height is 9. And then the last rectangle, the base is 1, and the upper left-hand height is 25. So if we take all that and add it up, we get 47.625, I believe, if I did it correctly. Again, plug that stuff in your calculator, you should be able to get that. So let's look at a right-hand approximation. So this time, again, the base is still 1.5, but this time we're using the right-hand y value, which is 6.25. I guess I'll put that in parentheses. 6.25. The second base is still 0.5, but now the right-hand y value on that one is going to be 9. And then the third base is 2. The right-hand y value of that one is 25. And the last base is 1, where the y value, right-hand y value is 36. And that one's going to give us 99.875. Again, I strongly urge you to check these yourself as you do them. Let's do the midpoint. So this one's going to be a little bit, I'm going to write this in a strange way. The base of the rectangles don't change, 1.5. Then it's going to be whatever in the middle. What's in between 1 and 2.5? 1.75, I think. So that's going to be f of 1.75. I actually didn't work that one out in a calculator like that. It's whatever you get when you plug 1.75 into x squared. Plus 0.5 times f of what's in between 2.5 and 3 is 2.75. And then the next one is 2 times f of, looks like 4. Well, that's 16. We could have plugged that one in, but whatever. And then 1 times f of 5.5. Yeah. And then if you plug all that stuff in, what I do know is that works out to be 70.625. And again, make sure you get that value. And then the last one would be our trapezoids. And once again, unfortunately with this, you cannot pull the bases out. 1/2 is 1/2. That is the same no matter what. We can't use that little shortcut though. So we have to do each individual trapezoid. Now, remember the bases are the y values in this case. So we're going to get 1/2, the sum of the bases, 1 plus 6.25, times the height, and the height was the difference in the x's, that's a 1.5 for the first one. Plus, the second trapezoid is going to be 6.25 plus 9, that's the sum of the bases, times the height, which was 0.5. Okay, the next one is going to be the sum of the bases of 9 and 25. The height there was 2. And then the last one was 25 plus 36, and the height there was 1. And I'm pretty sure that that one works out to be 73.75. Again, please do check to make sure that those values are correct. And this is the only one where so far where the trapezoids and midpoints weren't the same, but that's because the difference in the x's was different. So the bases or the heights, depending on which one you're looking at, was different. All right, 12 minutes, a couple minutes more than I thought, but good enough.